that 14 is the hardest of those three. Okay, and one of the reasons is, so when you think about work, you can't just think about it in terms of like, it's just an equation, right? It's a concept. And work is when you have a force that causes a displacement or hinders a displacement. And when we talk about work done, we can talk about it in a few different ways. And the easiest way, or one of the easier ways to think about it, is to think about net work. Because net work is equal to net force dotted with your. And you have to understand a couple of things here. If you're starting from rest and there's a net force acting upon you, then whatever the direction of that net force is the direction that you will move. Okay, if I start from rest and there's a force that pushes me this way, I'm going to go this way. I'm not going to go this way or this way. Right? That's impossible. That's physically impossible. If I'm already moving, there is a possibility that the net force can be in the exact opposite direction that I'm moving. But those are the only two options that exist for a net force. Okay, so for this case, they're telling you that there are three different forces, okay, and then they tell you that there's a 4-meter displacement, but they don't tell you the direction of the displacement, which seems like a giant nightmare, but it's actually not so bad. Because whatever I can figure out, whatever my net force is, right, let's say it's this way, it doesn't even matter. Then I know that my displacement is going to be in the same direction. So when I do this dot product and it's net force dotted with my displacement, it's either going to be cosine of 0 or cosine of 180. Okay? And in this case, because I'm starting from rest and then I'm starting to move, it's got to be 0 degrees because the force is helping me to move forward. So really, this work equation is equal to net force times displacement times cosine of 0 degrees, which is 1. Okay? So now all I have to do is find out the magnitude of the net force vector. Okay? And to do that, I have to add all the vectors in terms of their components and then find the magnitude of that. So what you've got is a vector which has some sort of f going this way, theta 3, and then you've got f2 with theta 2, and then you have f1, which so nicely is just in the x direction, right? And so there's a couple ways to do this. The easiest way is to write each one in terms of its component. So, for example, f1 is 5 newtons, so if I want to write it as a vector, it's negative 5 x hat, right? f2 is 9 newtons, and theta 2, whoops, I'm looking at the wrong thing. Sorry. This is 3 here, right? And then f2 is, nope, sorry. Is that right? Yeah, okay. And then f2 is 4 newtons, and theta 2 is 50 degrees. So f2 is 4, and theta 2 is 50 degrees. Okay, which means that this here is going to be 4 cosine of 50, and this is going to be 4 sine of 50. I know that because this is the opposite side and this is the adjacent side, so every adjacent is cosine and every opposite is sine. So that means the x component will be pointing in the negative x hat direction, and I'll have magnitude 4 sine 50. So it's negative 4 sine 50 x hat. And the y component is pointing in the negative direction, so minus 4 cosine 50 y hat. And then the f3 vector, 10 newtons, 35 degrees. So this is 10, and this is 10 sine of 35 and cosine of 35. So the x direction would be 10 cosine 35 x hat, positive, plus 10 sine 35 y hat, also positive. And then to find the net force vector, I add all the x's to get the net force x hat, and I add all the y's to get the net force y hat, right? And you probably get something negative x hat positive y hat maybe? Does anyone know?
You get 2.17 x hat and then 3.164 y hat.
3.164 y hat?
Yeah.
If I'm going to do these on the board, you guys should at least have your calculators out and try to do. Alright, so that's the net force, but it's not the magnitude of the net force. Now remember, when you take a dot product, there are two ways to do it. Either I take the x component of the force and I multiply by the x component of the displacement, and then the y of the force and the y of the displacement, and I add them together. Or I take the magnitude of the force times the magnitude of the displacement times cosine of the angle between them. Okay, so those are the two ways you do it. You can't like mix them together. It's either I'm doing magnitude cosine of theta, or I'm dotting each individual component with each individual component. In this case, you would think you'd want to take the dot product by doing the components times the components, but it's actually kind of annoying to do it that way because they're telling you that the displacement is 4, but they don't tell you the direction. So you'd have to figure out the angle and then figure out the components of the displacement in the x and the y direction. It's easier to do it this way. Okay, so it's easier to say, okay, I'm going to find the magnitude of the net force vector, and that's going to be the square root of 2.127 squared plus 3.164 squared. Right. And then the displacement is just 4, whatever they tell you. Okay? Are you going to do the last paper? Okay, so all the springs are over here. Try to read through it and just do it if you can. If you have questions, just make me stop talking, because I'm going to be talking for the whole time. Okay, so now, what is the magnitude of the force vector? I got, okay, yeah, 3.8 something, and that's the answer. Okay. Number 15 is kind of the same idea, except the displacement is all in the x direction, so only the net force in the x direction does any work. Is Natty out there? I would shut the door, but I'm so cold that I cannot shut the door. I'm sorry. We can't do it. So the net force is in the horizontal direction. So, I'm sorry, the displacement is in the horizontal direction for number 15. So that's the only component of the net force that we need to find. Okay, so what you would do for number 15 is you would say, well, here's the free body diagram that they've given you, right? But these vertical forces don't matter. It's only the horizontal forces that matter. So this is F2 and this is F1. So you would just do the next direction, okay, which I think turns out to point in the left direction, and the displacement is also in the left direction. So if you're dotting those two vectors, the angle is 0 degrees, okay? So then you should be able to finish that. What I'm going to ask you to do for this, since your homework for tonight is so simple, I'm going to ask you to go back and do these questions, okay? And then we'll turn them in tomorrow. That way, like, I'm kind of going over how to do it, but then you have to actually do it, all right? Instead of kind of watching me do it, I think it'll be better. And then number 10, let me give you whatever help I can with number 10. You have to find the components of the force vector and then just do the dot product. So like the displacement vector is 3, your displacement vector is 3x hat, y hat, okay? And then your force vector is, you have to figure it out by using what they've given you, 100 degrees and 2 newtons, okay? The other way to do number 10 is to say, okay, well, I know that my displacement vector is a 3, 4, 5 triangle, right? So this is 5, this is 3, this is 4, and then my force vector is at 100 degrees and it's 2. So I can take the magnitude of the force times the magnitude of the displacement times the cosine of this angle here, which you can figure out because this is 100 and this is 3, 4, 5 triangle, so it's 50 degrees. So then you can just figure that out. So that you could easily do it in both ways for number 10. In fact, you should try it in both ways just to see if it works. It is freaking out, I know. I know. Okay. So then that's the first 3. How about, assuming that you all know we'll do 41 together, 34, 61, and 74. Which of those do you think you need to do? Okay, I will tell you how to do 34 if you end up doing it. So 34 is a graphical analysis type question. They give you a graph of acceleration versus displacement, which is weird, right? You're not used to seeing things as a function of something that's not time, right? So they give you this acceleration displacement graph, and it looks like this. Okay. Now, then they ask you for the work done or something like that. We know a couple things. We know that if you have a constant force, you can use the work equation, which is just force dotted with displacement, right? But if you have a non-constant force, you have to use the integral form. Does anybody think that this is a constant force? Not. It is not a constant force. And the reason we know that is because net force equals ma, and assuming that the mass of the object is not changing, the acceleration is absolutely changing, right? So what happens is we can't use this. We have to use the integral form, which is the integral of f dot dx. And since this is like a rational problem, that dot product just becomes a nice, easy multiplication. Sorry, dr. I even did it without even thinking about it. The f dot dr becomes the integral of f dx. And you can do that every time you have a one-dimensional type of situation. Okay, and so the integral of f dx, area under a force displacement curve. That's what the integral is defined as. The area under the curve of this function when that's on the x-axis. Okay, and so we don't exactly have that. What we have is acceleration. Okay, but here's a good way to think about it. We're talking about force which is equal to mass times acceleration. So instead of writing f there, I'm going to write ma. And then we're going to say this number here, this mass, is a constant. And you can take constants outside of an integral. So the work done is equal to the mass times the integral of a dx, which is the area of that triangle. So then you take your mass, which is 10, I think, times this area, which is 80, and you get 800. Yes, ma'am.
I did nothing to touch about it, and I did it wrong. Like, if I just had work equals for them and master or semester, and then work from there now.
You are lucky that that worked. You're lucky that worked.
For that equation will work between plot and constant. You can solve the integral of acceleration.
Here?
Yeah.
Yeah, so you don't, I mean, when you say solve for it, what you mean is like, this is a triangle that goes from 0 to 8, and then, is that 8? Yeah, and then it goes from 0 to 20, so it's 8 by 20. So I'm going to find the area of that triangle.
You don't have to find 1/2 a squared. You don't do that.
1/2 a squared?
Yeah, like if the integral of it of a.
It's the same thing. Okay, it just so happens that this function, to find the physical area under this curve, I can do it perfectly by finding the area of a triangle. You know how you learn in calculus, like if this was like a curve right? Then you'd have to say, okay, well, I'm going to do like a little bit of a rectangle here, and I don't know how they teach it, right? Rectangle, rectangle, trapezoid, something, something, something. And then you'd have to count all the squares and like make approximations, but not if it's actually like a real shape, right? If I can find the actual area of this triangle, that is just as legitimate as finding out the function. This A is a function of X. The other way you could do it is say, I'm going to find out like a real true function, which is a y equals mx plus b kind of thing, where the intercept is 20 over 8. Right? So your A would equal the slope times x, and then I would take the integral of this function with respect to x, right? From 0 to 8. So then if I wanted to do that from 0 to 8, it would be 20 over 8, x squared over 2, evaluated from 0 to 8, and you end up getting exactly the same answer, which is 80. And then you still have to multiply by math to get x, or to get 4. Okay? So this is like way more complicated, still legitimate. Finding the area of a triangle, also okay. Okay. 74, I'm not going to do. I have to say no to at least one of them, right? I'm just going to say no to that one. 61, let's look at 61. Alright. I'll do 61, although, so I want to do 61 even though I did something similar in class, because I want you to kind of have a really firm understanding of the way we use calculus to find the work. So we're trying to find the work done by a force that is not constant, okay? So the force is not constant, and they tell you that the force is equal to 2x hat, well, I hat, whatever, plus 3y hats. And you're going from 2 to 4, 3. You're going from 2 to negative 4, negative 3. So this is my initial position vector, and this is my final position vector. Okay, the position vector, if it's a true position vector, what it means is that's the vector that points from the origin to a particular location. Okay, this position vector says I am at the coordinates 2, 3. Here I'm at the coordinates negative 4, negative 3. Okay, so to find the displacement vector, you would take your final position minus your initial position if you needed to do something like that. You don't in this case. So what we want to do, because it's a non-constant force here, non-constant, because it's a function of x, at least in the x direction, we want to use the integral form of the work equation, which says work equals the integral of f dotted with dr. Now, unfortunately, we've got like 2 directions here, so we can't just hand wave the dot product away like we did the last time. We have to actually dot f with the dr vector. And the dr vector is equal to dx x hat plus dy y hat plus dz z hat. Okay. So the work done by this particular force is equal to the integral of 2x dx plus the integral of 3 dy, and then the z hat goes away because there's no z component of your force. Okay. Now, where does this come into play? What does this have to do with anything? The boundaries of your integral. You go in the x direction, you go from 2 to negative 4, and then in the y, you go negative 3 to 3. Whoa! What I meant was the other way. 3 to negative 3. Everyone good with that? Sorry. You go initial to final. Initial to final. So then I can take 2 separate integrals. I can take the integral of 2x dx, which gives me x squared, and I evaluate that from 2 to negative 4. And then I take the integral of 3, which gives me 3y, evaluated from 3 to negative 3. And then when you evaluate your integral, you evaluate the upper bound first, minus the lower bound. So it would be negative 4 squared minus 2 squared, plus 3 times negative 3, minus, sorry for the mess here, minus 3 times positive 3. I did upper minus lower for the x, and then upper lower for the y. So it's 16 minus 4 minus 9 minus 9. And that gives you something, which I'm going to say is negative 6. Right? Thoughts about that process? $41. Just a moment.
You know, I thought I had it, and then I listened back to it. The second I thought I had it. I thought it was something real. I thought the problem was really simple, and then Andy came up and he told me today, like, you have to use like seconds and every time.
So here's the thing. I will be completely honest with you. There's an easier way to do this problem. And it requires knowledge that we're going to learn today. But I kind of want to show you this. You know what? Maybe we shouldn't do this. The process, but we won't do the whole problem. How about that? I'll show you. Yeah. So you don't need to do this question for your homework. If you remind me, we'll come back to it, and I'll show you the easier way to do it once we get to that point. Anyway. So here's the thing. What makes this so difficult? Why is it such a hard question? I mean, pick one reason why this is so hard. Yeah, that's the weird part, right? So you've got basically this force, and they give you the position as a function of time, which usually is exciting for you because that's going to be something where they ask me like, what's the acceleration? And you take the derivative twice, or something nice like that. But in this case, it's not helpful because they want to know what is the work done from t equals 0 to 4 seconds, and the mass is 3 kilograms. Now, time-dependent function. They work as a position-dependent function. So even though, first of all, you are all probably aware that we're not going to be able to just like dot two things together, right? We're going to have to do the integral of f dx. The good news is it's all in one direction, at least. There's that, right? So it's really not super vectory. It's just super calculus-y. So neither one of these things exists in our world right now. Yes?
This is, I was like, how come this can't, this is like, right, I think they take a little bit of acceleration and take one to the maximum acceleration.
Okay.
Then it's got the x and y and then it's put the...
All of the things you said are right. So what she just said, let's start with the first part. The first part she said, well, force equals mass times acceleration. I know how to get acceleration, right? So I take the derivative of this twice, and I get acceleration. So let's take the derivative one at a time, right? The first derivative of this is 3 minus 8t plus 3t squared. Okay? Then let's take another derivative, because this is equal to velocity, but what I want is acceleration. So if I take the derivative again, which is acceleration, I get negative 8 plus 6. And then I say, okay, well, net force is equal to mass times acceleration. So my force as a function of time, which is still weird, not exactly what I want, is going to be 3 times that whole thing. Okay, so it's going to be negative 24 plus 18t. I just multiplied 3 by the negative 8 and 3 by the 6. So that's where you kind of get stuck, because then you say, look, I found force. Isn't that awesome? And I say, that's sort of awesome, but we're not done yet. Because I can replace this with this thing here, and what I get is the integral of negative 24 plus 18t d which is still not what I want, right? I can't do that. If I said do this integral, you would say I can't do this integral yet. Okay, it's impossible because one, this is an function. you like the word implicit, huh? Yeah. Yeah. So this is implicitly a function of time. This is explicitly a function of time. I need to get this to be explicitly written in terms of time. So what I have here is dx dt. Why don't I just multiply by dt on both sides, and then I've solved for dx, and I can replace dx in this equation. So what I get is, if I multiply this by dt over to this side, dt, what I get is dx equals this dt, which is horrible. It's horrible. But that's what you get. So what you get is work is equal to the integral of negative 24 plus 18t dx, which is 3 minus 8t plus 3t squared. Now, from 0 to 4 seconds, I can do this integral. And when I say I can do this integral, I mean we don't have to do this. Yeah. Yeah, I mean, so what you would have to do, if you're going to do it the most difficult way, can you shut the door? If you're going to do it the most difficult way, you have to not FOIL this, because FOILing is too easy. You have to distribute this and multiply by all of this, and then distribute this and multiply by all of this to get a giant polynomial. The other way to do it is with something called a U substitution, because it turns out this is the derivative of this. So then you could do that. It would be really, really awesome and really easy. Okay, so that's the other way to do it. But either way, yeah, the math would suck, right? But it's algebra. You would have to distribute the negative 24 and then distribute the 18t, but then all of the integrals are power rules. So it's not like you can't do it, it's like we're not going to do it. Okay. But the idea, the concept behind taking something that is a time derivative or a time function and kind of morphing it into this is awesome, right? We just took something that was a position derivative and we transformed it into something that was a time derivative. Integral, sorry. Cool, right? Okay, that's all you need to know for that.
I just think it's fortunate how you wrote velocity as dx. It's like, I wrote it as v, and I would have never been able to, you know what I'm saying?
Mm-hmm. So. I do, and it was fortunate, but not like lucky. Like I did that on purpose because I knew that you would see that, and it would be better for you. I usually, when I try on the board to write like dx dt equals v equals whatever, so that you see all of it, or like this one d squared x squared equals dv dt equals a equals whatever. That way you can see all the different possible ways to represent what that means.
So if your problem is dealing with like the the position and time, you want to use every position and time.
That's a great way to think about it. Yeah, that's a great way to think about it. You want to like kind of boil everything down into the least number of variables possible. So hold on to this in your mind because we're going to come back to a much easier way to do this. All right. So today we're going to take notes on several different topics. Nick, how are you doing? Are you figuring it out? Okay. Thank you. Thank you for making my life easy. Are you ready?
No, I'm ready for all this.
So you guys, you're gonna have to be strong today. Strong. Be strong. But pay attention. Okay, and take good notes. We're doing everything today. We're basically doing the entire unit in one day. But the reason, I think this is going to work out. I think it's going to work out because none of the concepts individually are difficult to understand. It's that you need lots and lots of practice, so we're going to try to get like more and more difficult. But the reason I want to do it all in one day is because everything is so like interrelated and codependent. Like the problem that we just did, like if I had just taught you, a little bit more, we could have done it in a different way that would have been better. So I want to kind of give you all of the tools and then help you to learn to use them as you go. We'll see if it works out. If you hate it, then You can tell me after. Okay, so the first thing that we're going to talk about today is something called power. And power is directly related to work, which is, of course, related to energy, which is the unit of the day, apparently. And for power, we use the letter capital P. You can tell it's capital. I don't know how, but it is. Trust me. And power is a scalar. Okay. Does anybody know the units of power? Watts. So we've got watts.
What?
Okay, Bill Nye. We've got watts, which we use W for. What other units of power do you know? Horsepower is a legitimate unit of power. Horsepower. HP. Horsepower. I think that there are 746 watts in a horsepower. I have not used that number in at least a year, so if you want to check that, that's okay. You don't have to trust me. Something like that. It's something like that number. Any other units? Any other guesses? Electricity is not a unit. we use watts for electric power. Any other guesses? CC.
Like in Mario Kart.
I don't know.
Now I know.
Oh, for Mario, that makes sense because it's Mario Kart, right? I don't know. I've only played with it. That's like a volume. That's a volume. Yeah. I'll give you another one. Joule per second. That's a watt. That's the same thing as a watt. A watt is defined actually as a joule per second. So, but the reason I gave you this one is because I think that will help you to count. What do you know that's in units of joules? Work. And what do we know that's in units of seconds? Time. So, power is equal to work over time. So watts are a unit, this is work. So this is a unit and this is a variable. I know it's annoying, but that's something that you're going to encounter a lot.
How is that related to joule?
This is equal to this. Because this work is joules, T is units per second, a joule per second is a watt. So this W comes after a number. Like that light bulb is 100 watts. It's a 100 watt light bulb. This W goes into an equation because it represents work. This has units of work of joules, and this has units of seconds. So joules over seconds.
Can we make it do like a different time value?
You may do whatever you would like. I am going to use what the rest of the world uses, which is this convention here. But it turns out that this is not, because we are in calculus-based physics, this is an average quantity, right? It's how much work did you do over a certain amount of time, right? That the rate of that work could be changing, right? So this is an average value. So to write average, we put a bar over the top. Or you can put little AVG, like P subscript AVG. You don't have to do both. I'll do both so you can see them, but it's like double averaging if you do it like that. If you want to talk about instantaneous power, like what is the power output right now? At this instant. Instantaneous. It's just the same thing, but the rate, like the actual the instantaneous rate of change of something, right? It's the derivative. That's what it's defined as. So this is like your instantaneous power output of something that has a changing power output. This is the average power output of something. Okay, so let's talk about this for a second. Let's say that you're running up a hill. Me and Nathan are running up a hill. We're racing. I win, obviously. We're at Sonoma Canyon, last 3/4 of a mile. And so it's like this, right?
Actually, it's actually straight up, so.
It's mostly like this. So we're racing up the last 3/4 of a mile, and I'm winning. So I'm like, you know, it takes me, we both get to the top, right? We both get up here. This is me. And I'm fine, and he's like totally drained. And it takes me 2 minutes to get to the top. And it takes Nathan like 5 minutes, which is just fun. In reality, I'm pretty sure it takes me like 10 minutes to get to the top of that. Okay. Anyway, but I get to make up the question. So we're racing to the top, okay? And let's say that the elevation gain is like 400 feet, something like that. I think it is. So, and it's like 3/4 of a mile. Let's just use as many different units as we can here. I don't know. 1,200 meters and 300 meters. Okay. So, if I ask you, let's assume that we are the same mass, just for the purpose of this activity. If I ask you which one of us did more work to get to the top, what would the answer be? Why?
You did more work. Of power. Same work.
Same work.
Power.
Same work. Why?
You're doing the same thing.
You've got to explain it. You're right, but you've got to use the work equation, force and displacement, right? How much force do I have to exert on myself to get myself up a hill? Equal and opposite to my own weight, right? Okay? Let's pretend that instead I have like a harness and someone was using a cable to lift me up, which of course did not happen. But if someone was going to just lift me up at a constant velocity, I would get the force of tension would have to be equal and opposite to the gravitational force to lift me up. So that's the force, that's the amount of energy that I need to put into the system, right? The system being me. So I have to exert a force that's equal and opposite to my weight, and my displacement that's in the same direction of the force is this height, this 400 feet. Okay, and since we have the same weight, we have the same force and the same displacement, therefore the same work is done. When work is done on a system, that means energy is being put into the system. Where does the energy come from in this case? Yeah, your body, your muscles, right? I'm pushing on the ground, right? And so as I'm doing that, I'm lifting myself up and putting energy into the system, which is me. Okay. But if I ask you the next question, which is
for the first condition, is that just assuming that there's no acceleration? Like that would expect
I'm trying to decide if it matters. Yeah, no, it's assuming that we are both exerting the same force on ourselves.
So force is equal to mass, so get the same mass, and then so we have the same acceleration. But I get there.
Yeah, I'm trying to think of
Zero acceleration, constant speed, my constant speed slower than
Yeah, sorry, right. Thank you for putting that into. I was like, oh my gosh, I came up with a really bad example, but no, it is constant speed, but constant speed could be any constant speed, right? It means we have the same acceleration, which is 0 or whatever, but if we're going at a constant speed, it's just that my constant speed is different than yours. The net force is still the same. Okay? Which means that if we had zero acceleration, which means I had to be winning the race, right? Like I had to be going faster here already. And that's assuming, we came up with the whole thing. Okay, so anyway, so the work is the same, and how about the power? Okay, which one of us exerts more power? Why?
Because you do denominator and small.
Denominator small. Good. Okay. Questions about that kind of conceptual thing? Okay, good. Yep. Okay. But no, I kind of understand what you're saying. I'm a little worried that the force and the displacement are like when you walk. Let's imagine that my force that I'm exerting is always going to be like pushing me along the hill, right? And so that means that my force and my displacement are in the same direction. So the work done is just that now force times displacement times cosine of 0 degrees. So it could be at any angle and it doesn't matter. That's true. That's true. It does not matter if you go. If it works for you in your head. Okay. 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 So when we talk about work here, work is force dotted with displacement, right? If we have a constant work, or we're talking about some sort of average here, it's just going to be the force dotted with the displacement, right? And if we're talking about this here, you've got displacement divided by time now. So another way to write the equation for average power is F dotted with average velocity. Does everyone see where that kind of came from? Work is F dot delta X and then divided by T. If you just take the delta X divided by T part of it, that's average velocity. So if I take my force vector and I dot it with my average velocity vector, which are almost always in the same direction or opposite direction, then you can get the average power. Questions about power? Power is one of those things that comes up here and there, mostly on the multiple choice part of the test, but it's a good thing to understand. All right, that was the first topic of the day. Next topic. Energy. Energy. How would you define energy if you could? Huh? Okay, batteries are definitely a source of energy. Why? What is the form of energy that comes from a battery? Okay, so there's energy in chemistry. There's chemical energy. Okay, what else? What are the let's list types of energy. Okay. Oh, okay. Well, let's call that electric in general. Potential. Moving on. What's the most famous energy equation in the world? This is not part of the AP Physics curriculum. But don't you think you should know a little something? As a person who exists in the world, you should know this. You should know what it means. What does it mean? Okay, but what does that mean? Energy is equal to mass and speed of light squared. The energy of what?
Everything. That's not matter.
So we have this, you learn about this thing in chemistry called conservation of mass, right? And we learn about this thing in physics called conservation of energy, which is what we'll learn about today. What does the word conservation mean?
Not acid or destroyed.
Not created or destroyed, right? Turns out conservation of mass is kind of a lie. And conservation of energy is kind of a lie. Unless you consider this. That mass can be converted into pure energy, and pure energy can be converted into pure mass. You can, and we do it all the time. Okay, so that's a great example. In fact, that's way better than my particle accelerator example. Particle accelerator example. We collide particles at very, very high speeds. And stuff happens. You know what happens? Stuff flies, but where did it come from?
It's just magic.
It's not magic. So these high energy collisions can create particles and antiparticles at the same time. Out of nothing, out of energy. Those particle-antiparticle pairs immediately annihilate one another and create energy again. Okay, so you have kind of the two things. Energy, you can create mass. If you have enough, if you have a particle and an antiparticle, they will annihilate and disintegrate one another. Annihilate, like literally annihilate one another. There's no more literal term. Okay, it's like they actually disappear into nothingness, into energy. The amount of energy that they create when they annihilate one another is this much. The amount of mass that they each contain is the speed of light squared, which is huge. To be fair, that's a really, really small number in most cases, okay, but it's a really, really big number. What's a more everyday example besides your eating example?
The cause.
The sun, what happens in the core of the sun? What happens in the core of the sun? Fusion, nuclear fusion. And more specifically, what is most of the sun made of? Hydrogen. Okay? And into a bit. Okay? And kind of, this is like not a chemical equation, by the way, just so you know. We can never show this to anyone. So what happens in the core of the sun is something called the pp chain. It's really called that. The pp chain, because it's proton-proton chain. Okay? And it basically takes how many protons, hydrogen is a proton, basically, right? In the core of the sun, it's too hot for an electron to stay attached to anything, right? So it's all like just nuclei. And so hydrogen is just a proton. So it's the proton-proton chain. It takes how many protons or hydrogen atoms to create a helium atom? No.
3.
No.
4.
Yes. Why? Why is your face like that? I know why, but I want you to tell me. Oh. What's the atomic mass of helium?
2.
What's the atomic number?
3. 4.
4. Helium has 2 protons and 2 neutrons. So it's not like magically like 4 hydrogens just smush together and make magic helium, right? Because that would be 4 protons. There's like radioactive decay that has to happen that turns a proton into a neutron. Stuff gets crazy in the sun. So it takes 4 hydrogens to make a helium. And it happens in like a multi-step process. First 2 combine, and then something happens and one decays into a neutron, and then another one, and there's neutrinos everywhere, and like beta particles and all sorts of stuff. But this is the gist of it, okay? And what happens is this. The mass of 4 hydrogens is larger than the mass. That is the energy that's released in a nuclear fusion reaction. Same thing with fission. Okay? Because this has less mass than this, there is mass loss, that leads to the release of energy in the core of the sun, which creates this outward pressure, which keeps the sun from collapsing upon us. Okay? That happens, and then helium, this won't happen to our sun, but then helium will fuse into oxygen, and then oxygen will fuse into silicon, I think. And silicon will fuse into maybe one other thing, and then stuff fuses into hydrogen, fuses into iron. And when the instant that iron is the core of a
Boom.
they flip on the equation, okay? Then the one on this side becomes less massive than the one on this side. And then it takes energy to make the reaction happen. And because of that, all of a sudden the star like implodes and then explodes. And it's like instantaneous, and that's what a supernova is, and that's why the supernova happens.
So how do you get stuff bigger than iron?
Supernova. So the only way that any atom larger than iron in the periodic table has been created has been in a supernova explosion.
So why did you set back in the top?
Doesn't always necessarily create a black hole. You need to have a certain amount of mass to create a black hole. Sometimes it doesn't do that. Our sun will not supernova. Our sun will just go like and like just blow off the outer layers. It's kind of lame. No, it's like the instant that starts to happen. I don't know how many, but it's not like over a long period of time. It's like, we just used iron, everyone. It's time to collapse. Like, so, okay. Anyway, this, like I said, not part of the curriculum, but also probably the most awesome thing ever, right? Like, you can't know anything that's cooler than what we just talked about. I'm sorry. You could try to top that, but you can't.
Epic project.
All right.
Make the sun supernova.
So, you guys ever see the movie, what was it called, Sunshine? Where the sun was like dying and they try to send like nuclear bombs to the sun.
Does it work?
Really dumb.
No.
Okay. Okay. So kinetic and potential energy are the only two that we're going to talk about in this class. And we're not going to talk about all potential energies. We're only going to talk about like two different kinds of potential energy. Okay, that was my fault. But there are some things that you just have to know, and that's one of them. Okay, so energy is defined, like book defined, as the ability to do work. Okay, so if something has energy, then it has the ability to do work, either on itself or on something else. And let's start talking first about kinetic energy. When I say the word kinetic, what do you think of? Huh? An equation, okay. Movement. Okay, kinetic is the energy of motion. It's the energy of motion. We use the letter K, and the equation is 1/2 mv squared. I'm sorry for the lack of fanfare, but we gotta move it along. I wanted to talk about why and all that stuff, but it's just, this is what it is. It depends on mass and velocity. The faster something's going, the more kinetic energy it has. The bigger mass it has, the more kinetic energy. Okay, and which one of these two things and how much something has? The velocity, because it's squared, right? If I double my velocity, what do I do to my kinetic energy? Quadruple it. Okay, if this number doubles, then the whole thing quadruples because it's squared. Okay. Okay. We talk about. Oh, we're back to work already. It's because everything's related. Okay, when we talk about work. If we talk about net work, it's equal to net force dotted with displacement. Let's just assume that it's constant for now. And net force is equal to MA. Is everyone with me? And we're talking about this dot product when it's net force and displacement, then the angle is either 0 or 180, right? And so we're just going to say that the dot product becomes a multiplication. For the purpose of this derivation, which is what I'm doing. Let's go back 2 units to kinematics And let's look at this equation here. Do you remember this? Tell me you remember. Now, if I solve this equation for a delta x, I get dx squared minus vi squared. And if I plug this in for a delta x up here, I get that the net work is equal to m times dx squared minus vi squared. And if I pull out the 2 and do some algebra magic, I get 1/2 m dx squared minus 1/2 m vi squared. I made this a 1/2 out front, and then I distribute everything back in. I'm doing this really quickly because it's a derivation that you don't really need to like reproduce ever. I just want you to see where. This means something. What does it mean? What is this? Final what? No.
Power. Energy.
Final kinetic energy minus initial. When we say the words final minus initial, your brain should already be delta-ing everything, right? When I say final minus initial, that means delta. So we come up with this nice, concise equation. This is called the work kinetic energy theorem, which is incredibly clever, if I don't say so myself. Do say so myself. It's not, that's the point, it's not clever. It's like work kinetic energy theorem. Like it couldn't get any more obvious or dry or boring than this title. Not to always want to do the calculus derivation. It's always true. It's always true for everything. Yeah. This is always. Oh my gosh! Those words just came out of my mouth. It's always true for everything. I don't know. It's always true for everything. Okay. So let's go back. Let's look at number 41 for a second. Number 41. One of the things that we derived was the velocity as a function of time. So if we just plugged in the final time and the initial time and found the velocity at the final time and the velocity at the initial time, we could have just done 1/2 times the final squared minus 1/2 times the initial squared to find the work done. So you would have had to take a derivative one time and then plug in the final value and the initial value. That's the thing, right? I did skip the calculus derivation of this, which involves like implicit differentiation and stuff like that. But like this doesn't depend upon constant forces or anything. It doesn't depend upon anything. So when we were racing up the hill, Nathan, what was our change in kinetic energy? What was my change in kinetic energy? Anybody? What was it? It was 0, right? Because I said I'm not changing my speed. But it worked. Trust me, I did. I did work. But that doesn't mean that the net work on me wasn't 0. I did work, but so did something else. Gravity, which creates potential energy. Okay, so when I did work against gravity, which is how I run, I did work against gravity, what I created was a potential energy. Okay. Did what?
Supernova the sun.
You would do that.
Yeah, it's the afterlife.
Okay, so so when you do work on a force, you are putting energy into the system. Okay, and when you're putting energy into the system, you are creating a potential energy which can be converted into other forms later. Okay, so generally, you guys are lucky because I'm going to run out of time with all the really difficult stuff. But generally, there are two types of potential energy that we're going to talk about in this class. And that's not to say that there aren't a billion types of potential energy, right? There's potential energy that's stored in molecular bonds, right? That's potential energy. But that has nothing to do with this class. So in this class, we're going to talk about gravitational potential energy. And we use the letter U for potential energy, and I'm not really sure why we just do it. And that, the equation is mgh. And if you think about it, it's a force that you have to exert to lift something up at distance h. It's the work that you put into the system. Okay, that is put into the system. So if I lift this marker from the ground to a height of 1 meter, I put energy into the system. Okay, and it doesn't matter how it got here. I don't have to actually do it for it to have the energy, right? The energy is stored. And the reason that I say it's stored, I can use it to do something, to do work, right? I can allow gravity to do work on this marker and pull it back down to the ground. And as gravity does work on the marker, it's going to change its kinetic energy due to the work kinetic energy theorem. And it's going to convert the potential energy that it had up here to kinetic energy on the way down. That's why it's do that. Yeah.
So in other words, you enter the message to 0 and no network.
Yeah. Yeah. Energy is a scalar. Okay, so in this case, the reason you put a negative in front of your 9.8 is because we're talking about it as a vector. In this case, we're talking about the amount of energy something has. Direction has nothing to do with it. So you tell me. Positive. So, Lauren, I want to talk about that just one more second, what you just said. That's only true for what we call conservative forces. Talk about things like which take this type of energy out of the system and you can't ever get it back, then it does matter. Like if I did a closed loop like this, or if I did something like this, right? My displacement would be the same. But if there's friction and I do this, that's a different amount of energy lost than if I do this. Okay, so, and we'll talk about that probably next. So potential energy, so we've got this gravitational potential energy, and we also have what we call elastic potential energy. And elastic potential energy is derived directly from Hooke's law. You remember Hooke's law? Do you remember that it's a thing about springs? Okay. So the force from a spring is equal to negative Kf. And it turns out that in the same way that work is equal to change in kinetic energy, work is also equal to the negative change in potential energy. So work is equal to negative change in potential energy. Weird, right? But the reason I bring this up is because work is also equal to an integral of force and displacement. And if I tell you the equation for the elastic potential energy, you tell me if that looks familiar, or if you can make some sort of connection between these two things. This is the negative integral of this. This is why I wanted to do all this in one day, because it all is interconnected. Such a beautiful way. You love physics, everyone? potential energy is equal to negative work in the same way that I just wrote work is equal to negative potential energy. Okay. It's equal to the negative integral of F dot over V dot. In the same way that work is equal to the positive integral of F dot over V dot, potential energy is equal to the negative integral of F dot over V dot. And the reason for the negative is because in order to create potential energy, you have to work against a force, right? If I'm going to create a positive potential energy, I have to work against a force, and to work against a force, I have to go in the opposite direction of the force. Does that make sense? Okay. This equation has an integral form, and it also has what we call differential form. The differential form of the equation is like the opposite. It's like, so here's an example. When I say velocity is dx dt, or x is the integral of v dt, those are the same. Or this means the same thing. They mean the same thing. This is the integral form of this equation. It's also a form that will give you force from an equation for potential energy. For example, the equation for force is, just write it down. Those are not D's, they're called del's. They represent something called a partial derivative. You're gonna love it. I promise. You're gonna love it. You're gonna love it. Out yet? This is something you see every once in a while that you need to be able to do, and it's awesome. It's super fun, I think, to do. Here's how you take a partial derivative, and it's basically you have to undo the dot product, right? Because what you're doing is you're taking a scalar, which is energy, and you're getting a vector. How does that happen? In the same way that we dot product did, and we got two vectors to make a scalar, now we take one scalar and we make a vector. And the way you do it is, if I want to take the partial derivative of something, I take the derivative of that something with respect to x only times x hat. The derivative with respect to y times y hat plus the derivative with respect to z times z hat. Now what does that mean? Let me tell you. Let's say that my equation is 3x squared to the fourth z. And I want to take the partial derivative. This is just an equation. Oh yeah, sorry, they're positions. Yep. This partial derivative, I would first take the derivative of this function with respect to x. When I say with respect to x, I mean assuming x is a constant. Sorry, it's not a constant. X is the only variable. Everything else is a constant, including y and z. So to take the derivative of this function with respect to only x, I would multiply everything, 3y to the fourth z, and then take the derivative of the x part, which is 2x. Then I would do it again, but now the thing that I'm taking the derivative with respect to is now y. So it would be plus 3x squared z, 4y to the third, y hat. Then I would take it with respect to z, where z is my variable and the rest is constant. So it would be plus 3x squared y to the fourth times the derivative of z, which is 1. Not that bad. This could be way worse. It's like it's a prescription. You just have to go through and say, okay, I'm going to pick that x is constant, and I'm going to take the derivative with just x, and everything else just stays. Then I'm going to do y is the thing that I'm taking the derivative with respect to, and then z. You might see this once on your AP test. Yeah. You're taking the derivative of this function with respect to x.
But how can you do that when you switch one? That's what you do.
Yes. I was like, I'm not sure how to answer that, but just do it. You should just do it. That's how it is done. That is how a partial derivative is. All right. So the last part we're going to talk about today, and that is the idea that energy is conserved, which we've already talked about. Okay, and so basically we've got this idea that energy is conserved. What that means is the energy initial before something happens in a system is equal to the energy after something happens. Initial energy is equal to final energy. When I say energy, I mean all types of energy. Not just potential, kinetic. It could be things that are converted to chemical and then back to heat and then to mechanical and then whatever, okay? But when we talk about this class, you want to separate everything into two categories. One of them is mechanical energy, and the other one is everything else. So mechanical energy is potential and kinetic. Everything else is everything else, right? And in most cases, what that means is friction or resistive forces, that kind of thing. Things that make heat, right? Anytime you have friction, that's actually creating heat energy. And that heat energy can't really ever be returned to the system in the form of mechanical energy. So it's kind of lost, I guess, not in the same way that we say energy is conserved, it really is. But sometimes we want to convert to different types, okay? So when we talk about energy, total energy is split into two categories, mechanical energy and the work done by external forces. The work done by external forces is like when friction does work or you apply a force. Like, for example, when I was running up the hill, the Sabino Canyon Hill, I was applying an external force. I was supplying that force. Okay, so I was putting energy into this system, okay, converting like food energy to, muscle energy to whatever, which turned into kinetic energy. Okay? So basically I was converting energy I was adding energy into the system, mechanical energy. But I was doing it as an external force. In the same way that work done by friction takes energy out of the system, which you won't ever get back. Okay? So we have this initial mechanical energy, final mechanical energy in the absence of any external forces. Okay, so for example, imagine that you're on you're skateboarding and you're on like a loop kind of thing. No loop, what's it called? Dip, I guess? Not a dip. And you go off the edge here and skate, and you come up to here, and then what do? Go back. Okay, there's no friction, so we just kind of go back and forth. So up here I've got potential. Potential is converted to kinetic, back to potential, back to kinetic, back to potential, back to kinetic, back to potential, et cetera, et cetera, et cetera. So the total amount of mechanical energy in the system is going to be the same, but it's going to go all potential, some kinetic, some potential, some kinetic, all kinetic, all potential, all kinetic, all potential, all kinetic, et cetera. Okay? None of it will be lost to friction. So the total amount of mechanical energy in the system remains constant. But if there is friction, we know that I'll start here, and then I'll come to like here, and then I'll come to like here, and then like here, and then here, and then here. Right? So each time I make a trip, I lose mechanical energy because there's work done by an external force. and that work is negative, right? Friction does negative work, meaning it's removing energy from the system. Okay, I think that your heads are going to explode. Yes? Okay. So here's what I have for you. I have a packet